Hello, hello, it's Mr. Moydeen. Hope you are doing well in these tough times. Here's our second distance lesson dealing with separable first-order differential equations. That's a bit of a mouthful, so let's see if we can unpack this term bit by bit. A differential equation is an equation with a derivative in it. You know that by now. The first order means that our biggest derivative, our most high-level derivative in an equation is going to be a first derivative. So this just means that the first derivative is involved in a question like this. A second order differential equation would have a second derivative, a y double prime in it, for example. And separable is a class of differential equations that can be solved using a method called separation of variables. Basically, it means that you can group together x terms with a change in x and y terms with a change in y. So our goal is to achieve this, to get x's on one side along with dx and y's on the other side along with dy. So that's what it means to be separable. A little bit of backstory. In the previous lesson, we saw that the solution to a differential equation is whatever the original equation was, right? To get a sense as to what that solution might look like, we can make slope fields, which you see an example of here. It would be nice to get the actual answer rather than a generalization as to what the answer could be, right? One could imagine a curve following the trajectory of a slope field. That's a particular function. Can I find what that function is? And the answer is yes, using this procedure. So to get the actual original function, we're going to use this process of separation of variables. So steps are a little involved, but let's go through them and then do some examples. If the derivative dy dx is not by itself, if it's not already solved for, then you want to pause and do that first. So dy dx equals a bunch of other stuff. Once that happens, you multiply both sides by dx. This is separating your change in y and your change in x. So you multiply both sides by dx. Step 2 is very important. Step 2 is one of the harder steps. You need to use algebra in terms of balancing both sides to get your y terms, whatever they are, on the same side as dy, and your x terms on the same side as dx, and they need to be on different sides. So y terms on one side with dy, x terms on the other side with dx. Once you've achieved that, you're now ready to take the antiderivative. You're now ready to use basic or advanced antiderivative skill knowledge in order to actually integrate and get the original function. Each of those sides of your equation will spawn a plus c. So in order to simplify things, c is just an arbitrary constant. So if you combine one with another, you get another arbitrary constant, which for the sake of argument, we'll also call c. That just keeps it a little bit simpler. At this point, you have a couple of options. These steps can actually be switched. You could, at this point, start to solve for y and get y totally by itself with a c in it as well somewhere. Or you could use additional information if given, like a point to pass through, called an initial value, plug it in to your equation, and then find c, and then turn around and solve for y. So the order of these steps could vary. When you have not solved for y, when you have not solved for c, that's called the general solution. And when you have solved for c and plug it in, that's called the particular solution. So these last two steps are also quite important. So a couple examples. Given the differential equation here, find the particular solution. So that means we've got to go all the way through here with the initial condition 3, -3. Okay, so let's take our differential equation. dy dx is already by itself, so I don't have to do anything there. The next step is to separate my variables, change in y and change in x, by multiplying both sides by dx. And this will give me this. So the next step is to carefully use algebra to get x on the same side as dx and y on the same side as dy. So notice that these are already by themselves, or rather they're already on the same side. That's good. This y term here is in the wrong place though, so let's fix that. There are a couple of ways one could go here, but the way that I'm going to go is to multiply both sides by y squared. Why is that a good option? Well, I'm dividing by y squared here, so multiplying should fix that. And that would give me x squared minus 5 dx on this side and y squared dy on this side. Once you have gotten your x's with dx on one side and y's with dy on the other side, you're now ready to take the antiderivative. So let's go ahead and do that. If I take the antiderivative of both sides, once again maintaining equality, over on the left-hand side, I'm going to use the reverse power rule. So y to the second power, add 1 and divide, plus c. Over on the right-hand side, I'm going to do the same thing. X squared would be x to the third divided by 3 minus 5x plus c. As mentioned, these are both arbitrary constants, so I can rearrange them and get another arbitrary constant. So if I subtract, let's say, this c from this side, I don't know that these are the same things necessarily, so it's just some other arbitrary constant. So I get 1/3 y cubed equals 1/3 x cubed minus 5x plus some other arbitrary constant. So this is basically the general solution. I could at this point solve for y. I could do that and get a more precise general solution, I guess. But what I'm actually going to do is to plug in the given point earlier. We were told that f of 3 is -3. So our input is 3 and our output is -3. So I'm going to plug that value in to my differential equation right here. So I'm going to plug in 3, -3 for x and y respectively. And if I do that, all that remains should be a c term, which means I can find c. So 1/3 -3 cubed is -27 equals 1/3 3 cubed is 27 minus 5 times 3, 15 plus c. Over here I get -9. Over here I get +9 minus 15 plus c. A little bit of simple arithmetic, that's -9 equals -6 plus c. Add 6 to both sides, and you get -3 equals c. So what I can now do is go back to the step where I started plugging things in and go ahead and replace that with the value of c that I just got. So what I now have is not visible. Let's fix that. 1/3 y cubed equals 1/3 x cubed minus 5x. We've now found c, so -3. So our final step, again, I'm sort of switching up the order here. One could solve for y and then plug it in. One could find c and then plug it in. Either way, I have to solve for y. So let me do that at this point. I have one y right here. To solve for it, it looks like I could multiply everything by 3. That'll at least get rid of some of these fractions. That's always nice. So that will give me y cubed equals, multiply each one of these by 3. X cubed minus 15x minus 9. Take the cube root to get y by itself. And y is equal to the cube root of what we see there. And that's our very first particular solution to a differential equation, a separable first order differential equation. And that procedure is really what this video is about. How do you go through the algebra? What are some useful algebra steps that are needed? To illustrate that, let's do another example. This problem reads dy dx equals 3y cubed over x squared. So let's see what we can do. Multiplying both sides by dx gives us this. A couple different ways I can go here. I'm going to multiply both sides by 1/3y cubed. That's going to enable cancellation here and there. Again, y is with dy, x with dx. So that will give us 1/3y cubed dy equals 1/x squared, because that's still on the bottom, dx. I'm going to rewrite these things a little bit, and I think you'll see why. I'm going to rewrite the left-hand side as 1 over 3y to the negative 3, pulling that out of the bottom, and the other side as x to the negative 2. Since y and dy are together and x and dx are together, I'm ready to take the antiderivative of both sides. Doing so enables us to get, be careful with the coefficients here, 1/3 y to the negative 2 power, adding 1 and dividing by the same number plus c, and same deal over here, plus c. Consolidating my c's effectively means that I can just move 1 to the other side, as you saw. I'm going to simplify this a little bit before I start plugging in things, so that'll give us negative 1/6 for the constant, the coefficient, and y to the negative 2 power, I'm going to bring that back into the bottom, so that'll give us over y squared. So make sure you can recognize that these two things are equivalent. Over here, I have negative 1 over x. This dictates the sign, and then x to the negative 1 is 1 over x plus c. My given point, which was up here, is 3, 1. So I'm going to use that at this point to find the value of c. So plugging this in gives us negative 1 over 6 y squared, or 1 squared is just 1, equals negative 1 over x, which is 3, plus c. So simplifying, negative 1/6 equals negative 1/3 plus c. Add 1/3 to both sides. Negative 1/6 I can leave as is. 1/3 I'm going to rewrite that as 2/6 to make it least common denominator. And this will give us a value of 1/6. So we found c, it's 1/6. So let's plug that in. See if we can shrink this a little bit. So let's plug that into that brown step there, and this will give us negative 1 over 6 y squared equals negative 1 over x plus c, or plus 1/6. Okay, now we have to solve for y. That's going to be a little tough. We've got a couple options. Let's multiply to get rid of some of these fractions, and I'm going to actually multiply by the least common denominator. And if you recall from rational functions from pre-calc, the least common denominator can often be made, or a common denominator at least, by just combining all of your current denominators into one. So I have two sides of this equation. I'm going to multiply both sides by 6xy squared. So this term that I'm coming up with, 6xy squared, is a composite of my three denominators. 6 is repeated, so I'm just leaving one of them, x and y squared together. Oops, too much. So let's carefully cancel here and make sure that everything works out. So on the left-hand side, the 6 and the 6 on the bottom cancel. The y squared and the y squared cancel, leaving me with negative x. Negative 1x, I guess you could say. Over here, I'm actually distributing this to both parts. That's a key thing a lot of people make a mistake about. The coefficient will be negative 6. I think you can see that. The x will cancel, leaving us with just y squared. And over on the second term, the 6 and the 6 cancel, leaving us with x, y squared. Solving for y might be best achieved by factoring out a y squared, giving us negative 6 plus x, and then dividing by that term. We'll get y squared by itself, which means plain old y would be this. And there's our particular solution. One last example to bring it home. This one reads dy dx is equal to 6y over x squared. I'm going to do a slightly different strategy this time in terms of starting this. Rather than multiplying both sides by dx, which I could, you've seen that, I'm actually going to cross multiply. It's just sort of like having similar triangles or proportionality from earlier math classes. It's very similar. So I get x squared dy equals 6y dx, right? Let's see, x's with dx's, y's with dy's. If I divide both sides by 6y and also divide both sides by x squared, I'm going to get exactly what I wanted. Getting 1 over 6y dy equals 1 over x squared dx. This may look familiar to you in terms of what this looks like in terms of an antiderivative. You can tell I'm ready for an antiderivative because both sides have x and y isolated, separated. So let's go ahead and take the antiderivative. Over here, if I'm focusing on that part of the problem, I can rewrite this as 1/6 1 over y dy. What's the antiderivative of 1 over y dy? That's right. It's ln of the absolute value of y plus c. Over on the right-hand side, I'm going to rewrite that as x to the negative 2. And that's going to be add 1 and divide plus c. So my general solution is this, although I'm going to combine my c's together, and that'll give us that right there. I'm going to go one step further here a little bit just to clean this up. This term is negative 1 over x for the same reason it was earlier. And at this point, I'm going to plug in the given point, which is negative 2 comma e squared, and find the value of c. So 1/6 ln of y equals negative 1 over x plus c. So to solve for c, what is ln of e squared? Well, ln and e are opposite operations. Ln is log base e, so e to the second power is e squared. And you can check that with a calculator. This is 1/2. This is 1/3, 2/6. And solving for c would be 1/3 minus 1/2. So 1/3 is 2/6 minus 1/2 is 3/6. So negative 1/6 is c. Plugging that in to here will give us, let's use red, 1/6 ln of the absolute value of y equals negative 1 over x plus c, which was negative 1/6. So our final step here is to solve for y. Y is currently trapped by the natural logarithm. It's ln of y. So to get y by itself, we'll probably have to take an exponentiation step to raise something to a power. But let's first get rid of this times 6, times 1/6 because it's bothering me. So let's multiply both sides by 6. So now this is gone. Ln of absolute value of y equals negative 6 over x and minus 1, right? Because these would cancel. Okay, that's a little bit cleaner. So to solve for y, we need to get y out of the grasp of the natural logarithm. So remember, a natural logarithm means log base e. So if I raise both sides with base e, that load, these operations would cancel by default, giving me y equals e to the negative 6 over x minus 1. And we're done. Stay well.